No Starch Press, CBTS, CYBERARK, Booz Allen Hamilton, Dark RHINO Security, ENDGAME, RSA, and US Bank. Join the conversation. Tweet us at BSides. The presentation will begin shortly. BSides Cincinnati 2018 is sponsored by GE Aviation, No Starch Press, CBTS, CYBERARK, Booz Allen Hamilton, Dark RHINO Security, ENDGAME, RSA, and US Bank. Join the conversation. Tweet us at BSides. The presentation will begin shortly. BSides Cincinnati 2018 is sponsored by GE Aviation, No Starch Press, CBTS, CYBERARK, Booz Allen Hamilton, Dark RHINO Security, ENDGAME, RSA, and US Bank. Join the conversation. Tweet us at BSides. The presentation will begin shortly. BSides Cincinnati 2018 is sponsored by GE Aviation, No Starch Press, CBTS, CYBERARK, Booz Allen Hamilton, Dark RHINO Security, ENDGAME, RSA, and US Bank. Join the conversation. Tweet us at BSides. The presentation will begin shortly. BSides Cincinnati 2018 is sponsored by GE Aviation, No Starch Press, CBTS, CYBERARK, Booz Allen Hamilton, Dark RHINO Security, ENDGAME, RSA, and US Bank. Join the conversation. Tweet us at BSides. The presentation will begin shortly. BSides Cincinnati 2018 is sponsored by GE Aviation, No Starch Press, CBTS, CYBERARK, Booz Allen Hamilton, Dark RHINO Security, ENDGAME, RSA, and US Bank. Join the conversation. Tweet us at BSides. The presentation will begin shortly. BSides Cincinnati 2018 is sponsored by GE Aviation, No Starch Press, CBTS, CYBERARK, Booz Allen Hamilton, Dark RHINO Security, ENDGAME, RSA, and US Bank. Join the conversation. tweet us at BSides The presentation will begin shortly. BSides Cincinnati 2018 is sponsored by GE Aviation, No Starch Press, CBTS, CYBERARK, Booz Allen Hamilton, Dark RHINO Security, ENDGAME, RSA, and US Bank. Join the conversation, tweet us at BSides The presentation will begin shortly. BSides Cincinnati 2018 is sponsored by GE Aviation, No Starch Press, CBTS, CYBERARK.
All right, everybody, we running a little late here, so we'll get started. Here to present Coleman Kane to you guys. He'll be talking about Meltdown Spectre and the Voodoo of Speculative execution. So.
Yeah. All right, everyone. Find your seats. So before I get started on my talk, I wanted to just kind of remind everyone that we have this really neat CTF going. So if you're not familiar, a real popular thing at DEF CON and DerbyCon and some of the other star cons is Capture the Flag Challenge. A lot of times they're like super technical, and we definitely have some of that here, but I wanted to kind of give people an idea of what else we've got. So this right here is basically like you can log into it. If you go on our Twitter account, you can get all the access info and everything. As far as I can tell, I can actually get the Wi-Fi down here, so if you wanted to play in the audience downstairs, it seems like it works. They basically present a faux map of the world, and then you hover over any one of these things, and it basically has challenges and stuff like that. And apologies for the crummy resolution. My laptop screen is actually a lot bigger. One of the things I did want to point out is that a lot of these challenges are actually kind of trivia quizzes type things with a kind of subject matter leaning towards like InfoSec stuff. So the point of this is that anyone can play and anyone can win. You don't have to be a like network forensics or file system, you know, carver or anything like that in order to have fun with this. And that's kind of what we wanted it to be. So anyhow, with that, just wanted to let you know that that's a thing. I'll go ahead and close this now and get my presentation working. Oh geez, that's huge. Presentation. There we go. And then, awesome. So now we'll just hope my laptop doesn't fall asleep on me in the middle of the presentation, which I think as long as I do this is good. All right, everyone. So today I'm going to talk to you, not in super technical terms, but we will dive a little bit down into the weeds. Meltdown Spectre, which I'm sure that many of you saw in the news as the new sky is falling problem back in January, and then recently saw that it came back in the news again toward the end of April, early May, as it's alleged that there's a large number of more flaws. So these are CPU hardware flaws. You know, so basically architectural design issues that are inherent in a lot of the CPUs. So it was revealed, and I kind of expected this, that there's going to be more flaws of these types. They'll probably come up with much fancier, sillier names. So we'll wait and see. I was actually hoping a lot of the details would be released by now, but from what I understand, publication's been, I don't know, withheld or embargoed or whatever you want to call it, until late May. So while they get some fixes out. So I'll talk to you about these and why what they're going to release this month is the next step and why it's probably not the end, but just the beginning. So let's get started. So a little bit about me. I've been a security analyst for just about 8 years. So really, I think when I first started, got out of undergrad, they didn't really have information security as a career itself. I did a large amount of embedded system design and stuff like that, mostly focused around Linux platforms. I've been programming since before Gorillas.bash, if any of you are familiar with that. So that was probably one of my earliest toying around with programming exercises. I was a computer engineering grad at the University of Cincinnati, so it differs from computer science in that it includes a large amount of architecture, like CPU and operating system architecture work as well. And then I'm a PhD candidate, ABD, all but dissertation, just finished my coursework this month at the University of Cincinnati, where I also have put together some of their curriculum for their cyber classes. So one of the things I will say is that one way, as Danny had mentioned earlier in his talk, is find mentorship opportunities, try and get the knowledge that you've learned out. I've only been in security for 8 years. I've got a lot of knowledge to share and everything like that, and I try and get it out. One way that I do that is through University of Cincinnati, so I have taught some classes there. One of the great things about this school is that they don't necessarily presume to know everything. So they actually recruited myself and a number of other folks from the industry who didn't necessarily have a huge teaching background to help them put together some of the material they need to actually have a cybersecurity program that's informed by a lot of the people who do the work every day. So I'm also a contributor to a number of open source projects. This is just a handful of them, but 3 projects that some of you may or may not be familiar with. CRITS is an Intel database. Yara is the fancy Yara thing. Pattern matcher, malware analysis engine, whatever you want to call it. Extra grep. And then the FreeBSD project, open source system. That was actually one of my first open source contribution efforts. And I'll say that another piece, in addition to mentoring everyone, is get involved in these communities. Just a little tiny bit of contribution from you can go a long way to helping a lot of people's lives. So I list myself as a contributor to these things, but my contributions to them is probably 1% of what they do. And that's the same with a lot of the other contributors as well. And it helps out those projects immensely. And those are projects that, rather than me building my own version of everything, projects that can help a lot of people at a lot of different companies. So that's one of the things that I always like to stress. Get involved in that, because that's another way that we can all solve the problem together. So now to the actual subject matter that we're here to talk about. Meltdown Spectre. So WTF is that? So I just grabbed the information from the Meltdown attack. They actually have this nice paragraph that's really, really long. I will hit on 3 things that I've highlighted in red for you. So vulnerabilities in modern processors. So we're not talking about old stuff or anything. We're actually talking about stuff that's, you still go to Best Buy today and buy a laptop. Very likely you're buying vulnerable processors, vulnerable operating system. Allows programs to steal data which is currently processed on the computer, so data in flight. It's not necessarily going to be cracking the contents of your hard drive or anything like that, but it's going to be identifying anything that other people happen to be working on. This is where I think the point that Danny was making in the last talk about we all need to get familiar with doing threat hunting and doing, basically security work in the cloud, how the cloud's architected, how it's used, and everything like that. So we've become accustomed to having a lot of these dedicated systems where myself plus a handful of authorized users are what are responsible or what are running any code on the system. Nowadays, chances are that any single website that you're using today is running code side by side with something else that's completely unidentifiable to you, likely unidentifiable to the owner of the hardware as well. So random code is running on numerous systems in the cloud today. And you may be entirely unaware of it as well. I think, we had a conversation upstairs about the CTF stuff, the CTF website that we got running. And it actually references something that's hosted at googleapis.org as one of the UI visual elements or whatever. Random thing, completely unexpected, but is a part of that platform. That type of leakage into the cloud or leakage from the cloud is pervasive these days, and it is incumbent on all of us to understand how it works. So basically, they get a hold of secrets stored, so this kind of, repeats my point, secrets stored in the memory of other running programs. So we get started with what are modern processors? Because there's, going to be a lot of subjectivity about that. So the two things that I think are both applicable to these vulnerabilities and also the key features that most people are looking for in what they would consider to be a modern processor or a processor worth buying in a computer I want to buy today are these features. And I'm not going to dive into too much detail on all of them, but the big thing is superscalar architecture. So I give some details over here what that means, but in a nutshell it means that you can, if you're familiar with processor labeling, stuff like that, you might see it sold as like, 1 gigahertz, 3.2 gigahertz, that type of thing. So any of you familiar with like basic physics, that means, that's frequency. So that's how many times per second it does a thing, So in this case, superscalar architecture is how do I get the processor to run instructions at a rate that's more frequent than the gigahertz rating it's given. So there's a lot of circuitry for that. The other goal is how do I do it without 100% duplicating that processor, so making two of them basically. Can I get the same outcome, which is faster than the frequency, faster than the clock rate instruction speed, without fully duplicating the processor? Why would I do that? Because it's cheaper. It allows me to sell a faster processor at a lower price. The other piece that a lot of you are probably getting familiar with is multiprocessing, virtual memory architecture, and everything like that. So that allows us to run Microsoft Excel while I'm watching a video on YouTube, while my Facebook chat's updating, all of that stuff happening in real time. The critical things here I always feel is what we call time sharing support. So the ability for your programs to basically run in parallel behind the scenes without themselves having to be written to, say, hand off the processor to the next program manually. So the programs don't have to be pre-written for multitasking or multiprocessing. The other thing, virtual memory. The big thing here is that you can separate your memory out into basically privilege levels. You can have memory that's supposed to be where private stuff happens, and you have memory where, Facebook happens, or something like that, right? You don't want the two of them to be able to be to read one another, or necessarily, or at least you don't want the Facebook process, the Facebook memory, to be able to execute code that reads the private memory, your private key or something like that. So the objectives of these features are pretty clear, but I should say are desirable. But the critical one is this right here. Back in the day, you may have had, especially working in a scientific environment, you may have had computers dedicated for each one of the jobs that you needed to do. That's expensive, naturally. That's a lot of power, a lot of hardware, etc. The goal with this, always going forward, is can we figure out a way to gradually, more and more over the years, consolidate work that's done across multiple computers, multiple systems, into single systems? Can we, basically reduce the hardware costs while not losing any of the performance? That's the goal that most processor companies today are going after. In fact, most computing companies today are going after it. That's why the cloud exists. So the other piece, support concurrent computer users. That's where a lot of the memory protection I was talking about comes into play. That's where being able to divide up access control and memory and everything work. That's why that's important. That facilitates the idea of this public cloud where you can have Facebook living side by side with Twitter if you wanted, or your storefront sitting side by side with somebody's Minecraft server, that type of thing. You want to minimize real-world execution times by eliminating bottlenecks, increasing concurrency. So this means, reduce the cost of hardware over time while always seeing it going faster. Reason for that is we're always adding new features to software. We're always wanting something to do one more thing. Every time you tack on an extra bit of work, it takes that much more effort in order to get it done. So, this is the ideal. And I kind of set this here as like, this is the engineering mindset that's behind most of the consumer, hardware development today. This is the mindset that goes into a lot of it. Most of the time, and you may run into this in a lot of your places of business as well, at a management level and whatever, is that security is still reactive in this environment. So, in the words of the prophet, harder, better, faster, stronger. That's what they're going for every single year. They want you to keep buying more processors, more laptops, etc. Keep upgrading. And that's the way they get you to do it. So if you've ever looked at the, at the white papers or the, whatever you call it, the spec sheets for a laptop or for a CPU, if you build your own, that type of thing, you might have seen all these fancy buzzwords here. So every single one of these are actual build-ons, so they're not necessarily core to a processor doing its work. These are all built on or bolted on features that allow CPUs to do their work faster, better, harder, stronger, etc. I'm going to cover a handful of these because, to be totally honest, this is the type of stuff they cram into an entire semester of computer organization. But I'm going to touch on pipelining, branch prediction, shared cache, and speculative execution, and then probably touch on out-of-order execution as well. So here we go. So way back in 2005, and I bring this one up, I loved it, because this was probably the first indication that something was just not right. We were running ahead of ourselves, and we're building hardware without thinking of the ramifications of some of the features we're implementing. It also illustrates that, so this is 13 years ago. So it's actually, this mindset, this research is actually pretty old. Suddenly we had the Meltdown Spectre stuff pop up this year as if it came out of the blue. But if you go all the way back to 2005 and even before that, you'll see a lot of academic papers have been published on a lot of these research topics. So in 2005, Colin Percival, he published what's called a cache timing attack against the shared cache feature implementations in, I think at the time it was the hyper-threading feature that was in the Pentium, that was initially released in the Pentium 4 at the time. So I don't know if any of you remember there was a Pentium 4. It was very short-lived, not super successful. Actually, it was very unsuccessful. But they introduced this idea of, can we make it look like the computer has two CPUs even if it only has one? So can we do a lot of work in parallel by duplicating more components within the CPU without actually bolting another CPU on the motherboard? And they did this by duplicating some hardware, but not duplicating other hardware, such as things like cache and everything, which I'll get into in a little bit. Not duplicating hardware such as memory access and stuff like that. So the outcome of this results in accidentally exposing a mechanism to identify whether values are cached in memory or not. This is a timing analysis attack. It existed before this, but this feature, or I should say the concept existed prior to this. However, this feature made it very, very, very easy to exploit. So we'll jump into cache operation with a quick diagram. Don't need to understand all this. I'm not even sure how many people program in C these days. But basically, take this piece of code in as an example. So the idea here is that you have two source arrays. You're trying to do a matrix addition operation here. So you have two arrays, and you want to add all the values in each array, and then store those in a third array. So the way that most computers organize this is that these three arrays here are located in sequential memory segments right here. And then if you walk across it. So this basically goes from one, all the, basically from this one down here, this one down here, adds each cell together and then stores them in a cell right here. Historically, what would happen is your processor would Historically, what would happen is your processor would want to go and basically take one from here, add them together, store it here. Then take the next one from here, take the next one from here, add it, store it in here. The problem is that as processors got to be a lot faster, like pretend this guy is 3.2 gigahertz, memory is still a lot slower than that, maybe 1 gigahertz, maybe less, maybe 800 megahertz, something like that. I kind of gave a rough thing, maybe 10 times slower than the CPU. If I do that, I can only run as fast as my fastest memory. So to try and get around that, what they ended up doing was they came up with this idea of caching the data locally every time. CPU talks to this much smaller but much faster piece of memory that's actually attached to the CPU. And then what they'll do is the first time that the CPU wants something from A, all of A is actually loaded into the CPU's memory. And then from there, it basically walks through A by going back and forth right here without ever touching this again. So what happens is, if you end up having this CPU that's doing the work, and then you end up duplicating it over here with another CPU that's doing the work, and they're sharing this cache memory right here. If this guy retrieves memory from A, and then the other CPU tries to also retrieve memory from A, the first time it pulls the first element from A, it takes a long time. It takes memory time. It takes 10 times the speed to get it. The second time it wants something from A, if it's only going here, then it's immediate. It's fast. Whoops. This thing's a little touchy, apologies. So if you have a second CPU running over here that just happens to basically be waiting on A, it can learn that stuff is being read from A. Whoops. By looking and comparing the amount of time it takes to read something from A. So that seems innocuous at first, and we'll get into why that's significant. But anyway, I kind of wanted to give a real quick refresher on, or brief explanation as to how this works. The basic idea here is like, think of this as if I went to the grocery store for every single ingredient I wanted for a recipe, whenever I needed it at that moment, think of how slow that would be. That's why I go to the grocery store like once a week, buy all the things I need, and then keep them at home. This cashier is my home. That's the fridge or the pantry or whatever, and this is the grocery store. So there we go. So this kind of runs down a lot of what I was talking through in the diagram. I won't dwell on this slide too much, but the important thing here is that I can learn if something was read from memory or not, or if a particular address in memory was actually accessed by another processor, just by trying to figure out how quick or slow it took me to try and read something from that cell in memory. So the common attack techniques that are used for this, one of them is covert channels. So that's a way of communicating data between basically two processes that may be aware of one another, without that necessarily showing up physically in RAM. And the other one is private data theft, also known as snooping. So trying to steal information. So I'll leave this up here for a moment. This right here is the description of the math that works here. And again, this in itself is not the exploit. This is one piece of the exploit. Just to jump back here for a moment, there's a lot of features here. One of these features is invulnerable. The combination of these features creates a vulnerable complex system. So this is one thing that can leak a little bit of information that on its own right seems innocuous. So some attack mitigations. If you actually did feel this information was, important to try and prevent someone from seeing, these are some ways to work around it. Unfortunately, as you can see, every single one of them comes with some sort of penalty that takes away some of that ideal goal that I was talking about earlier. It makes it more expensive. It decreases performance, so it reduces the superscalarness of the processor. And that's why you see a lot of people who may be resistant. You see a lot of architectures that may be resistant to trying to implement things like this. Because every single one of them makes the processor a little bit slower, and as we all know, that's a very competitive market right now. So I'm getting to the next feature, which is pipelining, instruction level parallelization. So this is how you move from having a very slow processor that can execute maybe one instruction every few cycles to having something that can execute maybe multiple instructions in one clock cycle, you know, more than 3.2 gigahertz worth of work in a second. So many operations that you deal with or I should say many algorithms are complex operations that perform like multiple steps. So for instance, multiplication or division in a processor, that doesn't happen in one clock cycle. A lot of times that takes multiple clock cycles to work. Because of this, the CPU actually breaks a lot of those operations up into discrete steps. So you can think of it as like a recipe book or whatever, right? So in order to do a multiplication of two numbers, step one, get the first number. Put it on the table. Step two, get the second number. Put it on the table. Step three, do the sequence of steps where you put them on top of each other and do the multiplication work and everything, right? Step four, you have a result. Step five, put that somewhere. So remember, the computer's not really all that intelligent. It just does what it's told to do exactly very, 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 very well and very fast. So a lot of these units are designed to execute in parallel on staggered fragments of the original instruction. So this is a real common table that's built up. And some of you who may have taken CS or computer engineering or something like that might recognize it. But the idea here is that each one of these things is a component, so it's a circuitry, physical circuitry within the processor. I colored these things here to show you each of the instructions moving through the stages. And then this is time. So this is the first clock cycle. Or you can pretend this is second 0, right? Second 1, second 2, second 3, second 4. So this is a timing diagram basically. And then I have some details as to what these mean. But the idea here is that at the first second, or first clock, I'm fetching the instruction from memory. So I don't know what it says. I don't know what it's telling me to do until I actually read it. The second one, I actually need to decode it into what work that I need to do. The third second, I actually need to go to memory and put the stuff on the table that I was talking about, etc. The interesting thing about this is that if I was not to start loading in the next instructions while I've moved this one forward, I would end up with basically processor performance that's like 20% of my clock cycle, because I would have to do every 5 of these things before I could even start doing the first one, the first stage on the next instruction. The other thing that this reveals, and I think I have this on the next slide, is that by the time I get here, so 4 transitions in, by the time I get here, I am partially executing 5 different instructions at once. So I managed to approach my, maximized workload, which is, being able to run 5 things at once in the processor. But the other thing is that if we step here to like time 3, this instruction hasn't finished executing yet before I'm already starting to do work on the 3 instructions ahead of it. How do I even know that this one's worth executing? Because as we all know, you can have if statements or while statements. You can basically have like jumps and stuff like that in your code. I don't know necessarily if I'm able to run this. I'm actually speculating here. Or I should say the processor is actually speculating here. The processor just assumes that, oh, all the following instructions ahead of the current one I'm working on are probably going to be run. So, and I kind of lay that out right here. So the other thing too is that, so for instance, this one right here, or we'll jump to this one right here, right? So while this one's storing its result back into memory, instruction 3 is already loading the data that it relies on from memory, and then the second instruction already did that. So I've basically loaded data from 3 places while I've only completed one operation. So speculative execution. So we're going to speculate on speculation. So consider the following instruction sequence. And I didn't do assembly language. What I did is I turned assembly language into math for this. But every single one of these things reduces into an assembly language like, you know, instruction in pretty much every single architecture. And the point of this is that the vulnerabilities I'm talking about today actually apply across the board. So they're not limited to just your Intel processor. These are, you know, features that I'm talking about here that exist in every single CPU since like the Pentium Pro and the AMD 29K. So consider the following algorithm. This one seems pretty straightforward, right? So, you know, A is 1, B is 4, multiply the two of them together and overwrite B with whatever that result is. Then add them together, so add A and B together, and then store the result in A. So then by here, the original values of A and B are trashed, and B and A have new kind of combined values. Not only that, but A contains what you'd expect to be the result of the operation. Likewise, then store 5 in C, 8 in D. Do the same thing here, multiply the two together, overwrite C, and then finally take the initial one that was computed up here and then add this value here to get a final value for, say, the whole function. So getting back to how you can execute multiple instructions at once, that requires the processor to figure out what the dependencies are between all these. For instance, I can't do this instruction right here without first doing these two and this one. So I can't do it. So the processor needs to figure out those things. Highlighted in yellow are the ones that don't have what we call execution dependencies. I can load all this data into these 4 variables, into these 4 locations, without waiting on anything else in this program, in this very simple program. Highlighted in aqua are the ones that have minimal dependencies. And by minimal dependencies, I mean they don't depend on any prior math. They only depend on, again, let me get back to that caching diagram, right? This one. They only depend on this part of the CPU, the part that brings stuff out of memory and into the cache. Because of that, a modern CPU might actually choose to rework a lot of this stuff so that it can execute more of the work concurrently. For instance, because I can load large rows of memory into the processor at once in a single memory read operation, rather than doing all 4 of these as 4 separate memory read operations, how about if I just read all of them at once in one big operation here? So how about if I join them together? Additionally, what I've done is this operation down here actually moved up just above this one right here. So this little, whatever you call it, this little margin right here between the 2 lines, that's where this computation to get the end value of C happens. So I figured I'd show that there. The important thing is that this computation doesn't actually rely upon this at all to work. So you can, perhaps in this case, the processor has broken up the mathematical, you know, work into maybe 3 different pieces of circuitry or 2 different pieces of circuitry. So it can do these 2 at the same time. The interesting thing about that is when I wrote the program, my expectation was that I would do this work first, A equals A plus B. I would do that first before the processor does any of these 3. Right? That was how I wrote the program to work. The problem is that that's not how the processor made the program work. The processor actually made the program run this before this happens or these two happen. Which means that when A plus B gets executed, I have the processor has already done the, say, memory loading work for these right here and this. So what happens if this right here runs into an error condition? For instance, these two are not values that can be added together or something like that. The way I wrote the program, I might have had the assumption be that I can do all this work after this condition has been satisfied. It's, you know, if that operation is not invalid, so if that operation doesn't fail, right, it doesn't cause an error, then all this work happens. The processor reordered it so that that work happens no matter what. And then if this causes an error, the architect's concept, the architect's philosophy is that, oh, well, in that case, I just wasted my time. I did a bunch of extra work that I'll just throw away. That was the kind of architect mentality. And the benefit was that I can still have a faster processor. The consequence is that there is work that went into these that's based upon, say, another feature in the processor, the caching piece, that also leaks some information. So another piece that's here is complex array indexing. So this is the work that processors were originally invented for. So electronic computers originally invented to handle large matrix operations, basically to do your spreadsheets on the computer instead of by hand, right? So if you go all the way back to like the work that like IBM and NASA did and everything like that, it was tabulation work, large table calculations, things like that. So one of the interesting things, this gets a little bit into kind of memory nomenclature and everything, but one of the interesting things is that they came up with all these very complex ways to refer to data in a table. That's in a nutshell what all this is. So you can either say, oh, you know, if I have a list of numbers, the 7th number, right? I can even tell it to give me different data sizes for each one of those things. I can maybe have not just one column, but I can have columns and rows. So I can have maybe B tells me what the column is and C tells me what the row is or something like that. Ditto for this. I have a few simplistic things here. It actually gets quite more complex when you dive into the assembly language, and I didn't necessarily want to give an entire presentation on that. But in a nutshell, I have a bunch of circuitry built into the processor that allows me to do math on the indexes into my array in all sorts of complex ways. And some of these are native, so some of these are built in. Others are operations that I can create by stringing multiple different steps together, multiple different instructions together, such as this one. And that's left shift, for instance. Complex operation, leveraging, you know, the mathematical or arithmetic unit, plus, you know, some other work. So this is kind of, remember, we invented these things originally to do, you know, tabular calculations and things like that, not to play Minecraft or anything or Overwatch or anything like that. These things were originally created to do this stuff, basically do matrix math, do this stuff, very, very, very efficiently, and at very high dimensions. So this one is the one I'm going to hone in on for the next feature, right? And the next feature combines all of the things that we just saw in a very simple program to basically create the Meltdown vulnerability. So this is the one that many of the patches were pushed out for. You know, the ones that you saw, the emergency patches from a number of cloud providers and things like that, were pushed out to close this particular vulnerability. The middle of the night, like undisclosed Linux patches that went in that then were explained after they went in, that was these. All the super, or I should say the out of band non-Super Tuesday patches that went into Windows, this vulnerability. This is also the one that primarily affected Intel CPUs. So again, converted it and I simplified it a bit. So it takes a little bit more work than what I show up here, but at its core, it's 3 basic steps. So remember I talked about how you have the concept of privileged and unprivileged memory. You have the memory that is your private key, right, where that work's done, versus the memory that is your Facebook posts. So both of them are running code, both of them are running programs. We'll say that B happens to be something that is memory where your private key is located, something like that. And then we'll say that C happens to be memory where a random Facebook program is running or something like that. So what happens is, first, you may try and bring some data out of that privileged memory and store it in this variable X. Obviously, that's going to result in an error of some sort. Sometimes that error might just be to give you a junk value, give you an error code for this. Other times that might be to to cause what's called an exception or interrupt your program while it's running. The interesting thing about this is that if you get back to the pipelining thing that I was talking about back here, remember that by the time we get to executing by the time we get to executing that first instruction, we've already started doing work on the next 3, right? And this is a simplified thing. The architecture for your Intel chips goes much deeper than this. So we're actually executing maybe 15 or 20 instructions ahead of time for that. So let's get back over here. So basically what I mean is by the time you realize that you aren't allowed to read this data here, or I should say by the time the CPU realizes that, you've already started to do this work, and you've already started to do this work. And the processor identifies that right here, this work is also trying to reference other memory that's in your program space, that's in Facebook, Facebook's memory space or something like that. So right here, you're doing a very simple calculation based on this data. Inside the processor, they allow the speculative execution to pull this stuff out, bypassing a lot of the memory protections, the checks that determine whether this memory is supposed to be read by such and such process. Because again, their assumption is that they'll figure out whether or not the thing they've computed, the thing that they've retrieved, is something you're allowed to see after they finish executing this. And they'll just discard the wasted effort, the wasted work. The interesting thing about this one is that I'm taking a value out of here, right? I'm taking data that's stored in private memory, and then I'm using it to basically compute an index into another array that I know of. So it's not just an array that I can read data out of, it's an array that I pre-populated with data that maybe might be a unique value in every single cell or something like that. And then I'm storing that in Y. So this right here is something I'm allowed to see, right? I'm allowed to view this. I am basing the index into this, or what's called the offset. So I'm doing math here on the memory to basically pull out something that might be 4 steps or 4 slots in front of the beginning of this array, based on what was private here. So in a normal world, what happens is the processor throws a lot of this away after it decides that I'm not allowed to see the thing. In reality, what ends up happening is, right here, sorry. In reality, what ends up happening is that I've pre-cached the data right here, and I can basically go back through after I recover from this error, after I'm told that this didn't work. I can go back through and I can try and find out, sorry, the button isn't working. I can go find out which of the slots in this really big array come back very quickly to me. So which ones are a very quick read versus which ones are a very slow read. And by doing that, I can find out what value X was right here that I multiplied it by this number. And then I can find out what was computed here based on that. And that's kind of your timing attack in a nutshell. Is I basically will go through and try and read all the data in this memory region right here. and try and figure out which data comes back very quickly for me versus which data comes back very slowly. So, and then this is basically this is the very detailed explanation of all of that. So I figured it would be a lot easier for the audience to basically show you using the program there. But modern processes, you know, again, this is kind of the core thing here. Modern processes architected with the assumption that these internal details are transparent to the running program, that there's no way to actually know, basically they assume that I can't do what I just did. And that's because the whole concept of like memory timing and everything like that falls into the realm of something that's unpredictable, but not so unpredictable that it's impossible to say, judge within a certain, probability that you got the right answer. So that's kind of Meltdown in a nutshell. And as you can see, I mean, the code to do this comes out of the paper, right? I simplified it a little bit, but it's really just it's like, I think they have 7 lines of code and 5 of them are like execution. And 2 of the lines of code actually just make it a little bit more reliable. They overcome some other design issue that might end up causing it to be a little bit more unpredictable than normal. So, but anyway, that one was a pretty big glaring error, and it requires combining all of those different features together. So all those things that I just talked about that go into processor design, if any one of those had not been implemented, then this wouldn't work. And that's kind of the idea here is the culmination of many, many, many years of effort and people's little discrete good ideas kind of collecting together into a complex system that now presents a really, really, really glaring privacy flaw. So we get into branch prediction and Spectre, because that's, Spectre is very similar, uses a lot of the same logic that we talked about there, but then also uses what's called branch prediction. And those of you familiar with the exit 12 meme, this is basically how your CPU works, how your CPU speculatively executes anything that fits a model like this. So if there's a decision to be made, so as all programs can be broken up into a decision tree, in this case, the decision to be made is when I get to this test right here, do I execute this line at number 2, or do I start executing at what's in number 6 that isn't shown up here, right? Do I start executing past the end of this block? So again, we're going to consider A is a really large array, B is a really large array. A contains some data that maybe you don't, or I should say, contains an array of data that you want to expose to the program, but there's more memory around there as well that maybe the user's querying or something like that, or the program's querying that you want to keep private. So the branch predictor will keep track of the frequency with which a branch is taken. So if this was inside of a loop, it basically scores how frequently do we go from this line to this line versus this line down here. So if you're doing this loop, and let's pretend that A is a really large array, we'll say that A is like 1,000,000 elements or something, right? 1,000,000 minus 1 times it goes from this line down here, and then only 1 time it jumps all the way down here out of that. So that's what it means. It's literally basically a frequency test. And the reason why it's doing that is so that it can, getting back to the pipelining stuff, it can figure out whether it needs to start loading in these 3 operations, or if it needs to go from here and then start preloading the operations down here. That I didn't show because they're irrelevant for the case here. So if branch prediction is misidentified, so say on the last run here, when you get to the end of the array, it may already start doing this stuff with the character, with the data that's just past the array, the data that was not supposed to be read by the program. And again, it'll throw away the data because it'll realize, oh, the user really wanted to go down here, or I should say the program really goes down here. But this work is still done. And so we can take some of the stuff that was discussed right here, you know, we can take a very similar timing attack, timing computation, to basically try and figure out what's past the end of the array if we write this in a proper way. So this example that they gave, a really good use case for this might be if you end up having a program that's using like public key authentication or something like that, so a user's key ring, right? And that thing typically keeps some data private in memory. So this is a possible way to leak that memory out. This one's a lot less successful. This is also the one that's not patched. So if you remember when Meltdown Spectre was published, there was one patched vulnerability, or one major one that was patched, which was the Meltdown vulnerability. Spectre remains unpatched today because if you mess with this, then all of today's processors, basically if you turn this feature off, this branch prediction feature off, all of today's processors lose so much of their optimizations that they become so much slower. Even with the Meltdown patch, the impact was particularly noticeable for a lot of, for instance, cloud compute workloads. So those are my thoughts, and we're getting toward the end of it. I think we have about 6 minutes left. So things that I ponder. This has nothing to do with the presentation, but it is an interesting factoid. So the scary. So this is where it kind of gets to you all, in many of the different roles that you're in, want to be the solution to this problem. And this goes beyond just CPUs, right? This is kind of an engineering and design mentality. So many of these superscalar enabling features, so the things I talked about, they date back to the design of these two architectures from the big two CPU companies. They also exist, was it PowerPC implements a lot of the same features as well. AMD's 29K, which was predecessor to the K5, also had a lot of the same problems as well. But the important thing here is that many of you may not have seen these two chips since the 90s. That's when a lot of this was introduced. It was nearly a generation ago. So we're now living in a world where we've gone through, I think, like 5 or 6 generations since then. And the assumptions have been reinforced during all those development cycles that this is how you design a processor. It's no longer a like, oh, should I add this piece? Should I add that piece? It's now like, I'm not building a processor if I don't include all those features I showed you earlier. And we're constantly adding even new features as well. So all of those things are basically taken for granted as building blocks for a modern processor. There are likely more skeletons in the closet because, you know, this is coming up just now. It's just starting to show up on the radar. As a lot of you saw recently, there was a warning that I think this past week there should have been a large release of even more glaring flaws that were found by the same project team. Those got pushed off. I think they're supposed to be released later on this month. But in my opinion, I think that this is just the tip of the iceberg for a lot of this stuff. So the problem is, remember, there's no free lunch. A lot of these things came up because they're like, how do I get multiple instructions executing at the same time without duplicating my processors, which itself is the most expensive way to do it? How can I do it cheaper? How can I do it faster? How can I do it easier? That's the design mentality that's coming up with a lot of this stuff. Software flaws are easy to fix, easier than hardware flaws. Hardware flaws are more difficult, but now what I'm talking about is kind of the cultural common knowledge assumptions flaws. So this is not necessarily flaws that are in design, flaws that are in thinking. So take nothing for granted, assume nothing is ultimate. Don't presume that, oh, because this happened 30 years ago, it's been proven, it's been tested, I should never question it. That's not the mindset that you want to take. So this is kind of like what I call vulnerability model for complex systems. Every new feature introduces or adds to the probability of a new security or just design flaw in general. Every new optimization similarly brings this risk in. Time spent analyzing system integrity, fixing vulnerabilities, that actually carries a risk reduction. Typically, your engineering firms are investing in these top two primarily. We need to start figuring out how to measure this probability increase, this risk increase, which is not something necessarily done today. That's not a science. That's more of like an art or one of us pitching up here. We need to figure out how to measure these properties effectively using data, using recorded history, that type of thing, so that then we can build number 3 into the engineering process. Not just the hardware engineering process, because also software design flaws are introducing the same thing over time. But think about that. Every time a new feature, and we all know that with my phones or Facebook or Twitter or anything like that, you know, with, what is it? Facebook now implements a whole bunch of features to try and duplicate what Snapchat does, right? Like basically try and steal that market share away. They're all chasing new features and everything like that. But with every single one of those new features, they're introducing new code that may introduce new design flaws. It's not guaranteed, and it's very unlikely that it is ever going to be perfectly secure. We want to figure out how to build number 3, system integrity, vulnerability fixing, vulnerability hunting into the engineering process, because otherwise it's going to become more expensive or even impossible to do in a reactive mode, as we've seen with this guy right here. This is the reason why it's not unfixable, it's not practically fixable right now, because we've already installed all these things around the world, and chances are if we were to fix this right now, we would break the world. And that's not something we like to do. So with that, preguntas. Or I'll probably get kicked off because I took too long.